Hi everybody! For those of you who missed class, this is a video that covers what we talked about. In fourth block I had the students take notes because certain key concepts shown here in bold we're going to introduce today, but a lot of them are going to get developed and you'll have a more nuanced understanding of them over the next couple of weeks. So it's good to write them down so that you won't forget what they are between this time and next time, since we're also reviewing for AP. So go ahead and pause it and write these down if you would like to write them down. Today we'll do a couple things. We'll talk about what is a neural network, what different kinds are there, what kinds of problems can you solve with them, and we'll do the first step, which is understanding in more detail how they make their predictions. How they learn from data is a more complicated topic that we'll do next time. But before we start all that, let's remember the stuff that we talked about last time when you made k-nearest neighbor models. So the biggest new thing that machine learning does is, rather than have the programmer describe directly the process for how to do whatever problem the program is supposed to do, instead machine learning models learn from examples. So in order for them to do that, you need to train them by feeding in a whole bunch of examples of the type of input that they might be faced with, along with the correct answer for what they're supposed to output. And given those inputs and outputs, they'll change internally how they work so that when you feed them an unknown instance, hopefully they'll be able to correctly predict the right output based on the unknown instance. One of the things that's so powerful about that is now the programmer doesn't actually have to have a lot of expertise in the area for the type of program that they're writing. So for example, there was a startup that made a medical diagnosis classifier machine learning model that would look at CT scans and identify tumors as benign or malignant, for example. And none of the people on the programming team were doctors, and they didn't really even consult very much with doctors. Instead, they knew a lot about machine learning, and they were able to feed in the right data, and their model was able to outperform a lot of highly trained human experts. So that's what's nice about machine learning, is you as the programmer don't necessarily have to have domain expertise. So last time we also talked about the idea of a feature vector. Let's pretend that we're making a classifier where we want to predict what type of room in a house a particular room is. So like, is it a bedroom? Is it a hallway? Is it a bathroom? Well, the first step is you have to decide what kind of information are you going to give as input to your model for it to be able to decide what type of room it is. That's called the feature vector. It's a list of numerical data that describes different features of the input that you think are going to be relevant to classifying it as one type of room or another. So in the example we did last time, we imagined, what if we just gave it the two dimensions of the room, so like the width of the room and the height of the room. In that case, we have two-dimensional data, and this would be the training step where we feed it a whole bunch of dimensions along with the correct room category. And then later on, we give it an unknown instance, and it would use whatever we trained it with to try and make the prediction for the output category. So think for a minute to yourself, what if we were going to try and make a classifier where we give it some information about a person, and it will try and predict what that person's future employment will be, like what kind of job they'll do. Think for a minute about what kinds of information do you think might be relevant to that task. So in class, we came up with things like this. Maybe the person's age, maybe a Boolean value for whether or not they went to college. If they did, maybe their college GPA, maybe their college major, maybe some other stuff. So something to notice is not all of this data is numeric. Age is, college GPA is, but went to college is Boolean, it's yes, no. And college major is a categorical kind of data. So you have a lot of different college majors that all have, names. So for example, let's imagine a 22-year-old who did go to college, but their GPA was 2.8 and they majored in math. Rather than try and feed in all of this information the way that humans think about it, you have to represent all of the data numerically. So Boolean values you might represent as 0 and 1. Categorical data, you might just, like we did in the output here, come up with numbers that label each of the different categories. So math would be like the 36th possible major that we have in our list. So the point I'm trying to make here is the feature vector is the information you feed into your classifier, or more generally your model, and that it's important that it all be numeric. So if you have categorical data, you can still use that, you just have to convert it into a numeric form. Okay, so still in review mode, when we did the k-nearest neighbor algorithm, the representation that the k-nearest neighbor model used was just saving all of the training data. So we'd say that the representation was instances because it literally just saved all of the instances. And then the way that it made its prediction based on that was when you feed in an unknown input, it just compares that unknown input to all of the instances it saved and asks which ones is it most similar to. And whichever ones are most similar, the model predicts that the unknown input is the same category as whichever ones it was judged to be similar to. So finally, we're at neural networks. A neural network is just a different type of machine learning model. So rather than representing the information by saving all the instances of the training data, it has a more complicated or a different way of representing the training data. And because it represents the training data in a different way, it has a different process that it uses for making a prediction. So this picture right here is the type of thing you usually see when you look up neural network on the internet. Right now, I'm just going to tell you in a very high level, and we'll go into the details in a minute. But generally speaking, a neural network was inspired by brain physiology. So in the brain, you have neurons that are connected together, and the neurons send electrical signals from one to another, and somehow at the end of that process, you get something intelligent happening, we hope. So similarly, the way an artificial neural network is organized is you have a bunch of units, and each unit represents an artificial neuron. So you feed the numbers in your feature vector in, and you get one number per unit here. And then there's usually some hidden artificial neurons on the inside, and each one of these will combine all of the input numbers in its own unique way, and then decide what number to give as an output. So this neuron would take each of these three as an input, but it would make these numbers bigger or smaller depending on how important it thought each one was. And then it runs that through a function to decide what does this neuron give as an output to the neurons on the next layer. And this neuron that's one down from there would do the same process, but it might combine these numbers in a slightly different way, and then decide what number it would give as an output, and so on. So a lot more detail about this in a second, but the general point I'm making is that a neural network does solves the same kinds of tasks that our k-nearest neighbor algorithm does. It just organizes it very differently. Okay, so quick word of warning. Even though artificial neural networks were inspired by brains, they work rather differently from brains. So we are not literally simulating brains when you make an artificial neural network. You can think of it this way. The earliest airplanes were inspired by birds, but the principles on which they work are very, very different. So it's a loose analogy, but don't get too worked up about it. A lot of the students had said that they'd studied this kind of thing before. This is a kind of simplified illustration of a real neuron. So a real neuron generates electrical signals at the ends of what are called the dendrites here. And those electrical signals all combine inside the cell body. And then depending on how strong the electrical signal was, either nothing will happen at all, in which case there is no electricity that goes down the axon, or the neuron might send an electrical impulse that goes down the axon and then out all of these axon terminals. And all of these axon terminals are then connected to other neurons. Okay, so there's a lot. So this is like a very grossly oversimplified picture. Like I said that they're connected. They're not actually directly connected. There are some chemical processes that happen in between. But this is sort of a basic, this is enough for the computational model that we're going to use. So this is, I believe, anyway, this is a picture of actual neurons connected in the brain, and you can see that they're all kind of connected every which way in a manner that's difficult to discern here. So when we make computational models, we like to try and capture the essence of whatever it is that we're modeling and ignore all of the messy details. So when the original creators of artificial neural networks decided that they were going to try and model a neuron, this is how they chose to model the neuron. They said, well, computationally speaking, a neuron is something that takes some inputs and then combines them somehow and then decides how to send an output. So a single artificial neuron like this is called a perceptron, and we're going to actually make one of these later today. Again, there are lots of differences between this and actual neurons. So for example, actual neurons, there's no difference in the strength of the electrical impulse that gets sent out. What's different about different neurons is the frequency with which they're firing. Whereas in our artificial version, the output is going to be a number that could be bigger or smaller, but usually the frequency with which it fires isn't an important concept for an artificial neural network. So I'm going to stop mentioning differences, but there's lots and lots of differences. Okay, so another simplification is in the picture that I showed you, it wasn't obvious that there was any type of structure here. Actually, there probably is structure, but you can't really see it. Here in an artificial neural network, there's a very clear structure that's imposed on how neurons are connected together. So each circle here is the perceptron that I just talked about. It's an artificial neuron that can take some inputs and send some outputs. But all of the neurons are organized in layers, where your feature vector numbers all start here at the input layer, and then those numbers feed forward into the neurons at the first hidden layer. And then each neuron combines all of the numbers however it's going to. It decides what number it's going to output, and then the neurons at the next layer take those as the inputs. So for example, this neuron in the second hidden layer is going to look at the output of each one of these neurons, and it's going to combine all those numbers in whatever way it's going to, and then decide what output it's going to give. So that's why these networks are called feed-forward networks. It's because the information starts here in the input layer, and it feeds forward layer by layer until we get to the output layer. We're going to be making a classifier, which is just something that categorizes the input feature vector. And so what the neural network is supposed to output eventually is it's supposed to say which of several categories is the input feature vector. So that's what the output layer does. Each neuron in the output layer represents the probability that the input is actually a particular category. So if we're doing our room example, this top neuron might be the probability that the input represents a hallway. And the next one might be the probability that the input represents a bedroom, and so on. So each of these would output a number between 0 and 1. And then what you'd do is you'd look and see which one of these has the largest probability, and that's what you would predict as the output from your classifier. Okay, someone asked a question at this point, which was a great question. They said, do all of these probabilities add up to 1? And the answer is no. Imagine that we'd trained our neural network with a whole bunch of room data. And then we give it an input and we say, what if the room is 1 foot by 1 foot? What do we think that, what category of room do we think that is? It might very well end up being that this neuron would have a very small number because it's probably not a hallway, and this neuron would have a very small number because it's probably not a bedroom, and so on. So all of these might be very small if the input example doesn't seem similar to any of the training data. So just like k-nearest neighbor, and really any classifier, the artificial neural network is trying to generalize the input training data that you've given it. And if you feed in an input that doesn't seem to fit any of the training data, it might just tell you that there kind of is no category that matches terribly well. The reverse could also be true. So let's say you didn't feed it enough training data, or there are other various sort of ways that the training could have gone wrong. You could feed it in some input numbers, and it might say, oh, it's a very high probability it's a hallway, and there's also a very high probability it's a bedroom. So this could be like 0.98, and this could be 0.97. So if you were to add these up, that's obviously much larger than 100%, but it's because these outputs aren't intended to be interpreted as covering all of the possibilities and summing up to 1. So as an example of what this might look like for the digit recognition problem that we did before, remember we're feeding it in pictures of individual digits that are 28 pixels by 28 pixels. So we turn those brightness values into numbers, and then we organize those numbers as a single big list. So there's 784 numbers if you organize it in a big list. and each of the input neurons represents one of those brightness values. And then you'd have a hidden layer where each neuron combines all of those brightness values in some way and feeds forward. And in this picture, I've left off a lot of things, but typically everything in one layer is connected to everything in the next layer. And then as an output, we would have 10 output neurons because there's 10 possible categories that we're trying to classify. Okay, so that's a very high level kind of how neural networks work. And I know you're probably unsatisfied because you really want to know for real, and we'll do that in a second. Let's pause for a moment, though, and talk about what kinds of problems are neural networks good at solving. So we've already talked about classification problems. A classification problem is a problem where you're trying to categorize something or predict a category label. So for example, you could take an email and classify it as spam or not spam. Or you could take a picture of a digit and classify it as what number. Or more generally for handwriting recognition, take an image and classify it as being one of several letters or punctuation. Similarly, speech recognition, you might take portions of an audio clip of somebody speaking, and you might try and classify the data for each audio clip as being one particular sound or another. And those language sounds are called phonemes. Or image recognition. You might want to identify things in an image as being a person or a dog or a tree or a road and so on. A different type of problem that neural networks are good at is called a regression problem. So in a regression problem, you're predicting usually a real numbered value. So you're predicting a quantity instead of a category. So for example, if you were going to predict the price of something, like the sale price of a house, or the number of votes that a candidate is going to get, or the number of forward yards, or whatever. I don't actually know about sports. But some particular statistic about how a sports person is performing. That would be a real numbered variable, and so that's something you could make a mathematical model to predict. And you do this in math class a lot. Like these things should look, or at least this left one should look familiar, right? You've got all of this data, and you could come up with a model. You could say, let's draw a line that tries to fit the data as well as you can. And then if you had an unknown input, like what if it's 51, your line would predict what the output should be. So in other words, you are predicting a real valued variable. So in math class, you usually try and come up with these mathematical models by hand. A machine learning model can do the same thing, only you're not actually doing any math to figure out kind of what that function looks like. The neural network is doing all that for you. And I just wanted to point out that in math class, well, at least the ones that you've taken so far, typically you're only working with one-dimensional input. You could imagine two-dimensional input. So if you were going to predict somebody's income as a function of how many years they were educated and their seniority within the company. So all of these red dots would be the data. And if you wanted to keep the model simple, this is what's called a linear model because it's what a line would look like if it was in two dimensions. It's a plane. So that's a regression problem. And regression models don't have to be linear. You can have other types of curves in multiple dimensions. But again, when you're training a machine learning model, you yourself are not worrying about like what equation in multiple dimensions would fit the data as well as possible. Like what's happening internally is going to take care of that for you. Although the idea of linear versus nonlinear is still going to be important. Okay, so we're going to only talk in the next couple of weeks about kind of vanilla feed-forward neural networks, kind of a basic case. And some of the things that you've heard about in the news or you see about on YouTube or whatever involve fancier variations on this basic type of network. So I just wanted to mention briefly what they are. But all of this is to say that you should understand this thing before you start to dive into the variations. So one variation is called a recurrent neural network. What makes it different is it's not strictly feed-forward. So there are other nodes where the output from the hidden layer might feed to these nodes, and then the output from these feeds backwards back into the hidden layers. So recurrent neural networks are typically good for learning sequences of things, sequences of actions. So whenever you see those YouTube videos where they're like, hey, we trained a neural network to play this classic arcade game, probably they're using recurrent neural network to do that. And you may have heard of convolutional neural networks. These are typically used to classify images. And the last, and like this picture looks very complicated, but it's actually not that complicated. The very last step in a convolutional neural network is the basic feed-forward neural network that we're going to be learning about. It's just that there's a bunch of stuff that happens before that where there are techniques of trying to identify what are good visual features that you could feed in as the feature vector to your classifier, so that you as a human being aren't trying to guess what those features are. You're actually having part of the learning be learning what those features should be. And it's really cool. And we did stuff with convolutions earlier in the year, if you remember. We wrote the convolution kernel, and you use different ones to make, blurring and sharpening and all that. So you actually know enough code to implement all of this yourself, all of this feature extraction stuff. We're probably not going to because of time, but you could. And the final one the one that I wanted to say is sort of deep learning. Deep learning is kind of the marketing name for a neural network that just has a lot of hidden layers. And that's why it has the word deep there. Mathematically speaking, you could have a deep network with lots and lots of hidden layers. And in theory, you could create a neural network with a single hidden layer with lots and lots and lots and lots of neurons that's capable of performing in exactly the same way as the deep network. So mathematically, they're equivalent. But it turns out that the training process and some efficiency reasons mean that deep networks are kind of easier to work with in some cases. And what makes them special is similar to what makes convolutional neural networks special. For deep learning, so for the basic vanilla feed-forward network, you as the programmer do the feature extraction. You're deciding what numerical features to represent to send to your classifier. The deep learning network, the early hidden layers are actually learning what the important features should be, and then the later layers are doing the actual classification. And you might think, well, that's great. Like, why don't we just do that all the time? And the answer is, it is great. And when it works, you should do it. But they're also kind of harder to train than a feed-forward neural network is. And they also take a lot longer to train. So there's some trade-offs. Like, it is a good, powerful technique, but it's not necessarily always the one you might want to use. Whew. Okay, finally. So let's dive into the details about how the neural network actually makes its predictions. But we're not going to do it for a full network. Today, we're just going to do it for the building block of the network. So we're just going to look at a single artificial neuron, which I had said was called a perceptron. And rather than doing it in the abstract, you might think that you need a whole network in order to classify anything useful. Turns out that's not true. You can have a machine learning model that consists of a single perceptron, and it can still solve some important classification problems. So we're going to make a one neuron classifier that classifies a famous data set called the iris data set. And here it is. So it turns out there's different varieties of iris, and this beauty is called a setosa, and here's a versicolor, and here's a virginica. And they apparently look different. They have petals, and they have this other thing called a sepal, which looks like some kind of auxiliary thing behind the petal. It's not obvious how you would tell what the differences are, except that versicolor seems to have 4 petals, and the others have 3 petals. Unfortunately, that's not a number that we have in our data set, so our classifier won't be able to use that kind of dead giveaway. It will have to learn something more clever. Here's what our data set looks like. So we have a whole bunch of examples of different iris types. For each iris, we have the sepal length and width, and we have the petal length and width. So it's 4-dimensional data. We have 4 numbers. And then we have what the correct category or class label is. So this is what your perceptron model could look like. You could feed in all 4 numbers as your feature vector. And then instead of outputting which type of iris it is, you're just going to choose one type of iris, and it's going to be what's called a binary classifier. So we might choose setosa, and your neuron is just going to say yes or no. It is a setosa or it is not a setosa. You don't have to feed in all 4 numbers as your feature vector. You might choose to feed in just 2 numbers as your feature vector. And once you have this working, if you want to, as an extension, you could make your own very simple network where you create one perceptron for each type of iris, change it so that instead of outputting yes or no, it outputs a probability. And then you can do what I said, see which of these probabilities is largest, and then that would be the output for your classifier. So that's kind of available as an extension for you. Okay, so without further ado, this picture summarizes the mathematical details for how your neuron combines the input numbers and decides how to send an output number. A quick note, I've represented this here slightly differently than most other tutorials. Most other tutorials have an additional input called the bias. This was confusing for students when I did this last year, and what I'm presenting to you now was what we eventually arrived at as the thing that made sense to them. So we're going to do it this way. This way is mathematically the same. It's equivalent to having a bias input. But we'll understand it this way first, and then we'll afterwards go and look at the way that most people talk about it and see why it's the same. Okay, so let's talk through this diagram. So I'm imagining that there's only 2 dimensions in the feature vector. We're just going to give it sepal length and petal length. So x0 and x1 are both numbers from the input. I said that the neuron combines those numbers together somehow, and the way it combines them together is what's called a linear sum. So this w0 and w1, these are called the weights, and each of these is just a number that's multiplied by whatever the corresponding input is. The reason it's called a weight is because it kind of roughly is about how important should that particular number be in making the prediction. So if w0 is a bigger number, that means that whatever number the sepal length is going to be multiplied and going to have a larger effect in the overall sum. So the bigger the weight, kind of the more effect that the input numbers here are going to have when they get added together. Or, like, the more weight that input would be given in the overall sum. Okay, so you have the linear sum of the inputs, and that creates some number that I'm calling sum. Now you have what's called the activation function. The activation function is something that takes that sum as an input and then decides what it should send as an output. We're using a very simple activation function that's just a threshold function. So we look at that input number, the sum, and we ask, is it bigger than or equal to some number that's a threshold? So maybe 6. So like, is the sum bigger than or equal to 6? And if the answer is yes, we're going to output 1, which means we're predicting it's a Virginica. If it's not up to the threshold, then we'll output 0 for we're predicting it's not a Virginica. So in this simple perceptron model, there's 3 things that can change. Well, there's 3 parameters of the model that affect what it eventually outputs. There's the number that we use for each of these weights, and there's the number that we use for the threshold. So part of the learning process, which we'll talk about next time, is how the neuron will automatically adjust those 3 numbers over and over and over again when it sees that it got the answer wrong, so that hopefully over time it will get the answers correct. At this point, I had people break into groups and try a couple of problems. So the goal of this the worksheet here is a couple of things. First, to make sure that you really think through what does this process involve by doing it yourself. The second is to try and develop some natural way of thinking about what do the numbers for the weights actually mean. And then in the end, we know exactly the process that the perceptron is using for doing the classification. So because we know what this process is, we should be able to say something about what the data has to look like in order for this process to work, in order for the classification to actually work on the input data. So that's the thing that we'll end with. So you should go ahead and try this right now. So for example, let's say W0 is 2 and W1 is -5, and the threshold we're using is 0. Think about what would this perceptron classify an iris that has a sepal length of 4 and a petal length of 1 as. Would it predict Virginica or not Virginica? So I want to pause it for a second, and you should also pause it, and try and decide what do you think is your answer for A, B, C, and C here. Real answers in a second. Okay, fair warning, I'm about to show you answers. So the correct answers are A and C would predict Virginica, and B would predict not Virginica. Let's just look at C for a second. So weight 0 is negative 0.5, and the sepal length is 4. So 4 times negative 0.5 gives us negative 2. Weight 1 is 2, and the pedal length is 1. So 2 times 1 is positive 2. I add up negative 2 and positive 2, and I get 0. But the threshold is negative 1. So 0 is larger than the threshold of negative 1, so we output 1 for Virginica. So now that you've thought through that, here's a discussion question. If weight 0 is 2 and weight 1 is negative 5, and weight 0, remember, is about sepal, and weight 1 is about pedal, what do those numbers tell you in kind of natural human terms about sepal and pedal lengths for Virginica flowers? Here are some of the things that the students said. So one student said something like pedal length is more important than sepal length because the 5 here in this negative 5 has a larger magnitude than 2. So what that means is that the pedal length is going to affect the outcome of the sum more. And then another student disagreed, and they said, no, sepal length is more important because a larger pedal means that you're going to have a much smaller sum because it's getting multiplied by this large negative number. So that makes it a lot more likely that it won't reach the threshold and will be predicted not Virginica. So if you're interested in what's important to being a Virginica, the answer is if you have a long pedal, it's probably not a Virginica. It's probably like the sepal is more important in that sense. As a way of resolving that disagreement, we eventually ended by saying that a larger magnitude for a weight means that the outcome is more sensitive to that feature. So a small change in the pedal length is going to have a larger effect on the sum than a small change in sepal length because it's being multiplied by a bigger magnitude weight. But positive weight means that that feature is positively correlated with the category, or that the category that we're trying to classify is more predicted by larger values in that feature. But a negative weight means that the category is negatively correlated with that feature. So I was just trying to help you develop some more human ways of thinking about like what's really happening with all of these numbers. So finally, I asked the students to consider what if they were going to choose the 2 weights in the threshold by hand so that it was going to successfully classify some test data here. And students came up with all kinds of different things. Different groups did this in different ways, and a lot of them used the kind of thinking that we just talked about, so thinking about the relative importance of pedal length versus sepal length. Some of them ran some sample numbers. I want to show you a productive way of approaching this idea that's going to lead to a really important insight about this type of classifier. Sometimes it's helpful to think about data graphically. So here I've plotted in green the 2 Virginicas and in red the 2 not Virginicas. And the x-axis represents the sepal length, and the y-axis represents the pedal length. So I took the same data from the table, it's just that I plotted this is x and this is y. And we see this picture. Okay, so how does this really help us so far? Let's think about this algebraic process, but let's use the same labels that we did when we graphed the data. So what I said was, I was thinking about sepal length as being, I can't edit that, okay. Okay, so when we graphed the actual data points, I was using x as my sepal length and y as my pedal length. And let's look at the prediction of one of the groups. So one of the groups said that they wanted W0, well, let's do it this way. They wanted W0 to be -2 and W1 to be +2, and the threshold to be 3. And if you sort of do the math for each one, you can kind of see that that's going to work. So let's actually plug those weight values into the picture here as a way of helping us think about what is this algebra really saying graphically. So here's where we are so far. This general expression has turned into x times the weight -2 plus y times the weight 2 equals 3. And let's think, what do we do with this output sum? Oh, sorry, it's not 3, it's the sum. But then what we do is we ask, is the sum bigger than the threshold? So what we're really asking is this sum larger than or equal to 3? So if we do a bit of algebra, this actually is a familiar looking form. So instead of saying x times negative 2, I'll say negative 2x. And then if I add 2x on both sides and divide by 2, I end up getting y is bigger than this thing. And because you see, I mean, you could have guessed this originally. Here I only have a single power of x and a single power of y. So that's a linear equation. So if I was going to graph this, it looks like a line. Let's go ahead and look at what that line looks like. So what I said was I've got x times my weight 0, I guess let's do weight 0, plus y times my weight 1. And in order to predict that that's a Virginica, it has to be bigger than some threshold that I'll call t. So let's fill that in. And then we said weight 1 was going to be negative 2, and weight 0 was negative 2, and weight 1 was 2, and the threshold was 3. And there we go. So what are we noticing here? Green are Virginica, and the section that's filled in is all of the xy coordinates that our perceptron would predict as being a Virginica. And like, why is that? It's because we're asking what xy coordinates would make this equation true. What xy coordinates are larger than the threshold when we multiply them by these numbers. So any xy coordinate that's larger than the threshold when we multiply them by the numbers is in this kind of upper section. So we call this a half plane because the line divides the plane into two parts, and this is the upper half. And we know that it's a line because a single power of x and a single power of y defines a linear function. And more to the point, we can really visually see that this is working because the green are the Virginicas and it's in the Virginica prediction area. And the red is not Virginica and no red dots are in the green shaded area. So we have correctly separated our data into the two separate classes by a line. This is a really important concept. It means that our data is linearly separable. Linearly separable just means that the two different categories can be separated by a line. If we pretend that our data looks like this, so we've got two Virginicas and we've got two not Virginicas, I hope you can convince yourself that it's not going to be possible to draw a single line where both greens, both Virginicas happen on one side of the line and the not Virginicas happen on the other side of the line. And maybe we could sort of like, squidgy this around a little bit. But I hope it's clear to you that this isn't going to be a possible thing to do with a line. So this data is an example of data that's not linearly separable. And what that means is if we know that the data is not linearly separable in advance, we know that it can't be classified by a single perceptron because this rule is how perceptrons classify data, and this rule only leads to a linear boundary. So that's the other last piece of vocabulary. This boundary that separates the one category from the other category for how we're doing our predictions, that's called the decision boundary because it's the boundary that separates the two different decisions our perceptron might make about being one category or being the other category. So perceptrons have a linear decision boundary, but more complicated networks can have a much more complicated boundary. So there are a couple of caveats that I want to give you, or not caveats, but there's some tricks that you can use. So remember, our perceptron, we were only looking at 2 dimensions of the data. So we were looking at the sepal length and the petal length. So let's pretend that we have some data that's not linearly separable in 2 dimensions. Remember how, it wasn't Virginica that had the 4 petals, but let's pretend it was. Let's pretend Virginicas have 4 petals and all of the others only have 3 petals. We could add that as a 3rd dimension in our feature vector. So now every single iris is plotted in 3 dimensions. One coordinate would be petal length, one coordinate would be sepal length, and one coordinate would be how many petals. So in that case, what before wasn't linearly separable, in 3 dimensions you could draw a plane that separates all of the Virginicas from the non-Virginicas, because the Virginicas are going to have 4 petals and everything else is going to have 3 petals. So that's something to remember. If you add more features or you go up in dimensionality, that can give you enough room that it's possible to linearly separate your data. And there's actually another trick that we can use with the perceptron to make it have non-linear decision boundaries. So the perceptron could have a quadratic decision boundary, or a cubic one, or even a greater degree polynomial. We'll look at all of that next time when we actually dive into the code for making one.